requires a tremendous amount of energy. And this is the principle that drives that statement. Heisenberg, one of the old masters of quantum mechanics. Delta x, delta p greater than h bar over 2. Uncertainty in position times an uncertainty in momentum. 0.2 GeV times femtometer. What Heisenberg is talking about is it's impossible to know exactly the position and momentum of something at the same time. It's again a quantum mechanical idea, and one you're not used to, except in the way we are. Ever used a camera? If someone's running really fast and you take a picture with your camera, they look blurred in your photograph. So you know when you took the picture, where are they? They're blurred, they're spread out. You know time, but you don't know position. If I use very high-speed film and photograph that same runner, they're stopped. There's no blur. Now I can't tell how fast they're going. Right? It's from the blur that you can tell when looking at a photograph, if you know the speed of the film, how fast they were moving. So there are examples in the classical world of the same uncertainty principle. And the camera is just a nice analogy. This is a fundamental limit. As far as we know, no way out. On the other hand, it explains why at Jefferson Lab we want to go to very high energies, so 10 billion electron volts or 10 GeV, lets me get down to see a small fraction of the size of a proton. Really lets me see what's inside. This is a cartoon of one set of our microscopes. We call them spectrometers. In this cartoon, we have people here. So this is in our experimental hall A. Electron beam in, put target material in the center of our hall, and I can detect scattered electrons and scattered protons in these devices. This is what it looks like in real life. Cartoon, 2 microscopes, real life. A mess. But the target's still in the same room, and here's that spectrometer. It's the same device. Absolutely enormous. I need the really big to see the really small. I need very powerful magnets and detector systems. And this physically is what it takes. One thing that's great about this photograph is there's a big empty spot. And scientists love to build stuff for an empty spot. So back to the experiment. The idea they had in mind, send an electron beam in, detect a scattered electron, detect a scattered proton, and see what comes out. Does one thing come out? Lots of things come out. And that's where the blank spot is, where the stuff would come out. When I see a proton coming out, when I see a neutron coming out, what would I see? The idea required building new equipment, shown in a cartoon. They wanted a new scattering chamber, someplace to put their target material, a bending magnet, simulator, and a neutron detector. To detect protons coming out or neutrons coming out. We gathered the magnet from Amsterdam. This is it sinking into the Dutch soil. We brought it here, recycled it. A group in Israel made particle detectors for us. A group in Glasgow made more of our detectors. University of Virginia built a scattering chamber for our particles, and Kent State provide neutron detectors. So for all the experiments we do here at the lab, it tends to be a community effort, an international effort, getting scientists here, building equipment, let's set up an experimental hall. And this is what it looked like when it was all put together. So we have a bending magnet. So proton came back and be bent up and detected here. Neutrons had no charge, so don't get bent by magnets. Would pass through a lead wall and be detected in this back detector. So we had a great experiment to do electron in, electron out, protons going forward, and see what comes back. Are they protons coming back, neutrons coming back, to try and learn something about when particles are close together. They started in '87. We approved in 2001. We finally ran. It only took a few months to actually run. We had 3 PhD students, one from MIT, one from Tel Aviv, one from Kent State, here in Newport News. They lived here for over 2 years analyzing that data. They start with the information of charged particles passing through matter and turn that into physics quantities, compare theory, write theses and papers. So finally getting all that done. 3 PhD theses, an article in the journal Science, a physical review letter, all written up about what we saw. And what we saw surprised a lot of people, surprised a lot of scientists. So we came in on carbon, electron in, electron out, proton forward, and what we saw was always a neutron coming back. It was as if in carbon there were quasi-deuterons sitting there. The expectation was we'd see lots of proton-proton and neutron-neutron pairs. Real life was proton-neutron. That's why it was an exciting result. It wasn't what people expected. So we got a lot of press, and we tried to do a good job of explaining to others what we saw. And the importance, beyond this cartoon of carbon with a proton-neutron close together, this actually has implications all the way up to a neutron star. And this is a cartoon of a naive picture of a neutron star. It's mostly neutrons. And naively you go, oh, there are a few protons, they're not going to matter. It's mostly going to be about a sea of neutrons. What our experiment said is no, the protons really want to pair up with neutrons. So in a system like a neutron star with only a few protons, they're not going to just be sitting there doing nothing. They're going to pair up. They're going to play a very important role in a neutron star. That's a paradigm shift. And to this day, this has become a very important result and has been reconfirmed several times. So, from beginning to end, about a decade. So we did an experiment where we learned a little bit about what happens inside a nucleus with protons and neutrons coming together. It has implications not only for nuclear physics. That was pretty cool. But who cares? This is all basic research. And it's nice. It's nice figuring out what we're made out of. But is it worth all the time and energy and thought that goes into doing these experiments? Who cares? These are expensive experiments to do. So I'm going to give you a few examples of who cares. One, Kathy McCormick. She got her PhD here at Jefferson Lab and went to work for Homeland Security. This is a truck driving past something. Does anyone have a clue what that might be? It's a particle detector. Absolutely. If you want to know, in the trans containers that are coming through Hampton Roads through our shipping system, that there's no bombs, nuclear bombs, you need some way to detect it, and it better be fast. Because when you're working with business, time is money. Here's the idea. We put particle detectors that the truck has to drive by. At the same time, we're weighing the truck. We're either, if you do have a weapon in that truck, a nuclear weapon, we're either going to detect the radiation, its nuclear weapon emits radiation that we can easily detect with the particle detectors we use here at Jefferson Lab, or you have shielded it with so much lead, your truck's going to be way overweight. Either way, when I know something's funny, stop the truck, inspect it. So Kathy McCormick cares about nuclear physics. Who else? Gordon Cates, professor at the University of Virginia. He was very interested in something called polarized helium-3. He wanted to study the neutron. Helium-3 has 2 protons, 1 neutron.